go ahead.
All right. Chalk. Okay. So today we're going to be talking about the algebras. We're just going to review a couple of things that we talked about previously, but that we will need today. So, start over here. First thing, Lie group is something that's a group and a manifold. And in particular, the group multiplication and inversion maps are differentiable. This is not big enough. Okay. And the group homomorphisms are, differentiable maps. So we're going to call them rho today. So between Lie groups G and H, such that for any two group elements G in G, we have this property, or it doesn't really matter if you multiply before or after. This should all be familiar. Okay, so that was a review of things we already know. Now for review of things that some of us know. You mentioned you're in topology. Did you already cover connectedness? No. Okay, then we need. Okay, then things some of us know. Can you see here?
For homomorphism, do you not also need that the identity gets sent to the you need, I think, one more condition, which is either the identity
inverses.
Gets sent to I think the inverses get sent to
Yes, this is true.
And otherwise,
yes, I forgot about this. That is all. Okay. Connectedness. So now we forget about Lie groups for a second. This is just more general sense. I'm still going to say manifold, but it sets. It's also fine. So let M be a manifold. We say M is connected if there do not exist two subsets of M that are open, such that their union is equal to M and their intersection is empty. So basically, there can't be two open components of this manifold such that together they form the entire thing without intersecting.
So it's connected in the sense that I cannot disconnect it into two disjoint open sets.
Yeah.
The name makes it a bit weird, but continue.
Like intuitively, if you have like a kind of blob thing,
You can't chop it in half.
Yeah.
Yeah. Like you can do open set here, but this line still remains. Okay. So that concludes the things that we need to just start off this talk.
Actually, I guess, sorry, there's one other thing which you probably need to say is that the image of a connected map, image of a connected set under continuous mapping is connected.
Okay.
But, sorry, that was a confusing way to say it. But you can yes. Preserved under continuous mapping.
Okay. This is pushable, right? Okay, hold on. I don't want to do this. I want to do it like this. I've thought a fair bit about board order. Okay, so we're going to solve one of the exercises at the start of the covered section. So this is exercise 8.1. divided by exercise because the chapter is just also 8.1. But so the exercise is let G be a connected Lie group. I'm just going to abbreviate this because I don't want to write Lie group a bunch of times. Okay. And let U in the group be a neighborhood, so any open set containing the identity. And what we're going to do is we're going to show that U generates G. So basically this is saying that if you have any little thing just around the identity, you can multiply all of those elements together to eventually get the entire group, no matter how small that neighborhood is. So the way we're going to do this is, yeah, I did say connected manifold. So we're going to consider the thing that U generates. So we're going to call this thing S.
Sorry, so let's, I think there should be a question from the audience right now about something. What is the question from the audience? There's like a new word that maybe people don't quite understand.
Generates?
Yes.
I explained that already.
Oh, sorry. Never mind. I looked up on the board and I didn't see it. That's okay.
Okay. Where was I? Right. So suppose that the thing, we're going to say U generates something, because it must. And we're going to call that thing S. What we're going to do is we're going to show that S is both open and closed within the manifold.
Okay.
And so if it's open, it's open. If it's closed, the complement is also open.
Yeah.
So then the union of this S and its complement within the manifold will be non-intersecting and together be the entire manifold. But since the manifold is connected, one of those things must be empty, I should say. Non-empty. The manifold is always open within itself. You can trivially take the manifold and nothing, and that satisfies that. So we're going to show that there are two open sets that together make the entire manifold and don't intersect. So one of them has to be empty. Since U was not empty, it must be the complement of the thing it generates that's empty. Therefore, it generates the manifold. And that's just the approach, and we're basically going to spend some time showing that this thing is open and closed. Okay. So let X in S just be something in the generated set. Okay. Since group multiplication is differentiable, as we say over there, and because, okay, hold on. Okay, I'm going to say that. Okay. Group multiplication is the differentiable map, so this is still going to be a neighborhood of this, because you take open set to open set here. A neighborhood of X.
X times U is still a neighborhood of X. It's a bit more, it's not just that it's a differentiable map, it's that multiplication is a diffeomorphism. Because it's a diffeomorphism, it would send an open set to an open set.
Right.
So this is, it's not just because it's
I'm just going to.
And the fact that it's a homeomorphism, diffeomorphism is a lot. It's just enough the fact that it's a homeomorphism. But that's the consequence. So you may have heard in your topology course that a homeomorphism sense like kind of preserves all the open sets.
Yeah.
So if U was an open neighborhood, multiplication by X in the Lie group, that's diffeomorphism. It's a homeomorphism. So that is also a so X applied to, if I push U by multiplication through X, then that will still be an open set.
Yes.
Because multiplication by x. There's some.
Okay. So we have this neighborhood of x, but then we notice that xu. Hold on, is it clear what I mean when I say xu?
X, the group operation times u.
Yeah, it's just you multiply everything by x on the left. But xu is a subset of s, right? Since everything in u is in u,
Yep.
x was generated by things in u. So we just multiply by things in u again. You're still going to be in the thing that u generates, which is s. But since x is arbitrary, this implies that S is open, since every point in it has a neighborhood that's contained within the set. Cool. So we prove S is open. Okay. Now, instead, let Y be in the complement of S. Suppose that this neighborhood intersecting S is non-empty. So I'm taking something not in this generated set, and I'm saying, okay, I take this particular neighborhood around it. I suppose it actually touches the generated set. We're going to show that's not possible. Because if it intersects, then there exists some z such that yz is in S, right? Just by saying this. Okay. But since I don't have a notation for generates, sorry. Since u generates S, oh my God, I keep losing myself in my paper. Okay. Since u generates S, S times the inverse of Z is still just equal to S. Right? Does that make sense? Because you just multiply by a thing inside of it, and that's fine. Groups are closed. Okay. So since SZ inverse is in S, and YZ is in S, well, these two things combined, they lead you to the conclusion that Y is in S, but Y was not in S. So there's our contradiction. So actually, this cannot be true. Therefore, YU intersect S is empty. And so for every point in the complement of S, we also have a neighborhood. So now we've shown that this is open. And now we apply the argument that I said before I did any of this. We have our two open sets that make up the entire manifold, the entire Lie group. And therefore, one of them must be empty.
So you were doing G without S?
Yes.
Maybe do a slash like this instead of like this.
Sorry.
Because this looks like
Right.
a mod. And that's.
It's been a second. Okay. Did I do that anywhere else? No. Okay. So yeah, that concludes it. Therefore, G is equal to S. Then we win. So we have shown that U generates G. Any neighborhood around the identity element will give us the entire Lie group. And then the book says some things. So since you can take any neighborhood around the origin, sorry, not the identity, and get the entire group, it kind of sort of follows from this that the action of any Lie group homomorphism on said neighborhood will basically determine how it acts on the rest of the group as well.
Let's say this a bit simpler. If I can generate my whole group just out of some information around the identity, then probably all I need to care instead of trying to say something about the whole group, let's just look at stuff happening around the identity and then study that. And if I know everything about what's happening around the identity, then I'll know what's happening everywhere around the group, right? Because I can build the rest of the group out of it.
Not so.
Well, spiritually, yes.
Okay. I don't want to write all of this.
Not much more.
I don't want to write all of it down, but like let's say you want to know what happens at somewhere arbitrary in the group. You know that this set U is going to generate somewhere, and you can get to that point. Yeah.
Is that generation unique?
No.
Probably not. Like, what does generate mean? Generate means I can get this element by multiplying a bunch of elements from the open set together. Yes, and so I could maybe pick different combinations.
Yeah, like for example, if I take just additive group of integers, I can add numbers to get to 5 different ways if I start with 1 and 2. Yeah.
Thank you.
But the point is you can get there. And remember this property, right?
Yeah.
So if you know if the thing you want to get is x times y times a bunch of other things, and you know what happens to x, y, and a bunch of other things individually, it doesn't matter whether you multiply before or after. You want to get the homomorphism after, you can just do the homomorphism first, and then multiply everything together, and then you get what you wanted. So if knowing what happens in a small neighborhood around the identity is good enough, well, how do we know what happens in a small neighborhood around the identity?
So one comment about you writing stuff down. This is good, but right now we just had our key idea that we want to look at stuff around the identity. You have a piece of red chalk which you can use and write down the big idea of just like one sentence. We look at stuff around the identity somewhere.
Here's good.
I think that's perfect. What is this reading group put out?
Nothing. Okay. I'm going to new board now. Okay. So how do we know what happens near the identity? Well, that's kind of what derivatives are for, right? So basically, more than half of the rest of this is just going to be taking a bunch of derivatives and doing weird things to them. It should hopefully not be that bad, but that is basically what we're going to be doing. So it is time to draw a picture that I've definitely not seen before. Okay. Different color. So let's say this is our starting manifold called D. We do, what's a different shape?
Square.
Too pointy. That's nice. And that's the manifold we want to go to H. And we've got this homomorphism between them, which we're going to be calling rho for basically the entirety of today. If we're going to say that these are the respective identity elements, somewhere vaguely in the middle, and we're saying we want to know what happens in a really small neighborhood around the identity. And honestly, we don't even need that much. We only need the derivative at said identity to know what's going on near it, vaguely, sort of. The book doesn't really do this like fully, but it's good enough. So we're going to.
The book will do this later.
Yeah. So we are going to look at tangent spaces, because that's where all the derivative stuff lives. Rapidly running out of colors. Okay. And we're basically going to ask the question, well, okay, this is a tangent vector. We have some underlying map on the group here. This tangent vector should, in some sense, go to somewhere here in the other tangent space. But we don't really, like, derivatives. How do we do this? And can we express all the information we need about the Lie group in terms of this tangent space? Because you have, thanks. You have taken linear algebra. Vector spaces are nice. These Lie groups things may not necessarily be so nice. It would be great if we could, represent what's happening in the group in terms of the vector space. So we are going to attempt to do something like that. We are going to attempt to do exactly that.
Yeah. And so what's the like? And I'll just say what you said again. Like, you have some manifold, right? And you want to figure out the information about some open neighborhood around the point, right? Well, what's the point of a manifold? Is that I can approximate it with Rn, right? So locally, it looks like Rn. So if you just tell me something about the tangent space at that point, well, then that tangent space on its own already like kind of approximates the region around the manifold, right? like if I have a sphere and I want to know what's happening like around the point, well, just the whole point is that like a single tangent plane kind of approximates a little bit that part of the sphere. So hopefully we can just like think about just the tangent space at a point eventually.
By eventually, we mean like
Right
now, with no further justification.
Yeah.
Okay. So the book gives two principles. We're going to say the first right now, and the second soon after. Both of them mostly without any justification, but like just it sounds about right, so we're gonna roll with it. It is correct.
Well, with a lot of intuitive justification,
Yes.
which sounds a lot right because we know how the derivatives work and what they do, and then we'll have proper proof later.
So, first principle the book says, I'll start over here. So let G and H be Lie groups where G is connected. The connected bit is important because like we have all of this nice stuff about the entire structure of the manifold, but that only works if the manifold's in one piece. Like we can't cross gaps.
Okay.
The whole exercise relied on being connected. Yes?
Maybe it'll be answered later, but why only G connected?
What do you mean only G?
Or unless he's about to write like both L and G and H connected.
So, no, you just need G to be connected because you
The
want
domain.
to yes, domain. Why? Yeah, why should only the domain be connected?
If you're not connected.
Right? Like the point was, like, what are we trying to do? What's the goal?
To be able to describe H using a local neighborhood around it.
I don't want to describe H. I have a map row going from where to where?
G to H.
G to H. And I want to describe the map row to you. Okay? And I know that, wait, if I know how rho acts on a little neighborhood of E, around E, then I can figure out how rho acts everywhere on G. Right? Because I can get all of G using the little neighborhood around E. And then it's a homomorphism, so I can just expand the product. Okay. So that's the point. You only need G to be connected, because the goal of what we're trying to achieve, we're trying to describe how rho acts, how rho maps G into H. You know, what H is doing is whatever, as long as it's a Lie group and rho is a Lie group homomorphism. But G has to be connected because I need to be able to get all of G from the little neighborhood around it. And sometimes it's not connected, but when it's not connected, it's okay. We can figure stuff out anyway.
If it's not connected, just look at a part of it that is.
Yes.
You'll be fine. You'll learn it in topology.
Yeah.
Okay. So a map rho from G to H is, importantly, uniquely. I should not write there. Determined by its differential at the identity. By the way, my handwriting, if I'm writing in lowercase p, which I will not today, I usually cross it because rho is hard. So anything that looks like a p and isn't in a word is a rho.
How do you write rho?
Like a P.
Okay.
Maybe I should like add a tail.
So I think, in my opinion, it's easier to write rho the other way. Instead of starting from the bottom like this, start from the loop like this, and then it looks better. But okay, this is like no.
Yeah. Okay. So let's see. Yeah, and oh shoot, I should have written this. But the differential is a map between tangent spaces at the identity. Why is it a map to the tangent space at the identity of H? Because that's how homomorphism works. They always send identity to identity. It follows fairly quickly from the initial definition. I just won't do it here. Why am I writing using this? Okay. And that's the first principle. Second principle will be coming on later. And I'll write it down there. Okay. So let's see. Right, okay. So from this thing, Lie group homomorphisms rho, they give you a unique map of vector spaces. The derivative is unique. This is your map of vector spaces. Ta-da. Okay, but if you have two like Lie groups, then which like linear maps between their tangent spaces, because there's a lot of them, as you might know, which ones actually come in this form? When do they arise from some underlying row? Right, that's a more difficult question to answer. And we are going to try to answer that today. Because like these group homomorphisms, intrinsically they carry the information of the group along with them. So there should be something that we can embed into the tangent space that will tell us what was happening with the group to begin with. And we are going to spend the next hour or so trying to define such something. And that's called the Lie bracket, which we will spend the next hour doing. Okay. And before, I'm going to write down the second principle, which has a bunch of words that we don't know yet. So let G and H be Lie groups. That's just going to be true for the rest of this. I'm not going to bother. And G is connected and simply connected. What is simply connected? Should I explain it?
I should probably state it.
I did not prep the definition, but okay. If you have a loop, you can shrink it down to a point without getting caught on anything. That's the intuitive explanation. So if I have like a donut, right? Can I draw a donut? Okay, I'm gonna do it like over here since we're not. Okay, if I have this donut shape, and I've got this red loop kind of running through the middle of it, I can't shrink this down to a point, right? It'll get caught around the hole in the middle. So the donut is not simply connected. A circle is also not simply connected because you draw a circle on the circle and you can't do anything. It's still a circle. You can't get to a point. So
yeah, just a small side comment is like, while we are requiring like this group to be connected, and then in this other case this group to be connected and simply connected, the thing that we're going to define at the end can be defined, without any of this connected, simply connected stuff. It's just this is like more kind of motivation for why we want to give these definitions. That in these very nice cases, it gives very nice.
Okay. So, and we're going to say a linear map of like between these two spaces has the form of like D row at the identity for some homomorphism from G to H, if and only if it preserves I'm going to write this in a different color. Lie bracket. And I don't know why I capitalized bracket. So this Lie bracket is basically going to be something that we can put in the tangent space that will tell us everything we need to know about the group for this kind of purpose.
So the bracket an operation, like a function.
It is. Yeah, preserve, like, we talk about, okay, actually, I'm going to use the word preserves a lot later, so that'll be clear from context. But I'm going to, should I use this space? I guess I'll use this space. Okay, I'll keep that up for the rest of this. Okay, we're through page 1.
Yeah, so I'll say some more words. So in the first principle, what did we say? We said that, okay, if I have a homomorphism between one Lie group and another Lie group, right? And this Lie group can kind of be created out of something around the identity. Then, to fully specify this map row, all I need to tell you is how the tangent space of the identity here gets mapped to the tangent space of the identity there, and somehow that like tells me everything about this map. So the claim there is that this map between Lie groups contains the same information as some linear map between the tangent space here and some tangent space here. So we like the whole homomorphism is completely determined by some linear map between tangent spaces. And with principle 2, we're trying to ask the opposite question. Suppose I had a linear map between tangent spaces. arbitrary linear map. When is that a linear, like when does this linear map actually come from some homomorphism of mapping the underlying Lie groups, right? And so the claim is that, okay, there's actually like this Lie bracket thing, right, which can be defined on these tangent spaces, and this Lie, so for this to be a homomorphism of Lie groups, then this Lie bracket thing has to be preserved by these linear maps. Okay. And so in some sense, this Lie bracket is like the final piece that fully captures the Lie group structure, just at the identity. So there's like some structure on the tangent space of the identity, which fully captures the Lie group structure, but it's just on the tangent space of the identity.
Okay.
Keep going.
So I've said we have a thing, we're going to have a thing called the Lie bracket that is basically going to tell us everything we need. So we need something that can actually encapsulate all that information. So we're going to start at the group itself and try to translate the group structure into the language of the tangent space, which is going to be somewhat involved and involve multiple derivatives. But we're going to start very simple. So how do we find information about the group? Well, if I tell you how to multiply everything inside the group, then you know everything about the group, right? Group elements are basically determined by how they interact with each other. So if I tell you how they do that, then you know everything. So multiplication would be a great starting point. But this has a bit of an issue, right? We want to talk about tangent spaces, and ideally we'd like to think about just one, because this Lie bracket is going to be intrinsic to the group itself and its algebra, sorry, its vector space, its tangent space at the identity. So we'd like something that actually stays within the tangent space. This doesn't, right? Because if you fix some g and your h is something that you take free, you're never going to stay at the same point, right? If you multiply by something that's not the identity, you have no fixed points. So we're going to instead use something called conjugation. This is not an English class, but it's basically, so the conjugation map is going to be denoted by an uppercase psi, subscript g. And if we input an h, this is, g and h are both group elements, by the way. They both live in the starting space. H is not here, just to clarify. But this is going to be defined as g times h times g inverse. Yes, I did that in the right order. And now we can see if we set h to be the identity, this is in fact a fixed point, because then g inverse cancels out, and we stay where we began. So this is where we're going to start building our Lie bracket. So great, but this is entirely in the language of the group, which is not very useful to us because we want to work in the tangent space. So how do we go from something to its tangent space? We take derivatives. So I feel like I'm really going to start wanting an extra board. This is not movable, is it? Okay, I hope this is simple enough that I don't need to keep this visible all the time. I'm going to pull this board back.
Actually, I would rewrite what conjugation is again on the new board.
Yeah.
Start using the new
Okay.
board.
Okay, surely we don't need this. We know what these are.
Yeah,
We're done with this basically after going through that. Just remember, connected this is like it's connected and like, yeah.
Also, note how fun it is that like so far every picture that we ever drew this whole video group was always the same picture. And I feel like it will be always, it's almost always the same picture. Well,
Well, it's not.
there are other pictures that can be drawn in geometry.
So GHG inverse is conjugation. That's where we're going to start. Okay. So importantly, homomorphisms, the definition is gone, but they respect multiplication, right? Doesn't matter whether you do it before or after. Conjugation is basically just multiplication again, so homomorphisms respect this, which is, we also want that, right? if your thing doesn't respect homomorphisms in a group, it's probably not very useful. Okay. So I was going to say we're going to take differentials. So this is a thing which is called, the book calls this adjoint representation. Don't worry about it. And the thing after this, it doesn't even give it a name. I'm just going to write the symbol and not worry about it. So we're going to define a map. Let me write this over here because I'm not that tall. Okay, so capital AD. And it's a map from the group to the automorphisms of its tangent space. So do we know what this is? Okay. So the automorphisms of this tangent space is just a vector space, remember? And we're just going to pretend it's real for intuition purposes. But basically, this is all the ways that you can have invertible linear transformations from the tangent space to itself.
We're not pretending that it's real. It is real. The vector space is always real. It is possible that you could have a vector space that has complex numbers in it, but you always think of it as a real vector space over the real numbers.
Okay.
Why is it real? Because remember, your tangent space is you have Rn coordinates, and then you have directions in Rn, essentially. And directions in Rn, that's always a real vector space.
Okay.
So always real.
Okay, it's real now.
Always real.
So this is now Rn.
Yes.
It's all the ways that you can, linearly transform Rn into itself and be invertible. You have taken linear algebra. Yes.
Automorphisms are all the invertible homomorphisms from the space to itself.
It's a set of transformations.
Yeah.
Yes. So maybe you should write that if you can try and reach up. Yes. Because we'll need automorphisms and we'll need maybe
Yeah, but yeah.
In this case, it's the same. So it's just that automorphisms is a more general word. You can say automorphisms of a group, and that will just mean all the invertible homomorphisms, not invertible maps. Just say
linear?
All invertible homomorphisms.
Okay, sure.
Because people say automorphisms of groups, automorphisms of any space that has some structure and notion of homomorphism.
Yeah. Okay.
In this case, they're invertible linear maps.
Yeah. So if you go to itself, why is this true? Okay. Okay, where was I? So we are here. Right, this thing. And what is it actually? It's given by lowercase g maps to the differential of conjugation by g at the identity. Okay. And this is in fact a tangent space map, which was implicit in the stuff I wrote before, but we're just going to say that.
So yeah, so you have that map, right? You fix G, so then it's a map from the group to the group. Do you agree? So it's just some differentiable map, and so you just take the derivative of the identity. Note that GHG inverse. Where does that send the identity? Where does conjugation by G send the identity? If I substitute the identity, we'll do it again. Into the conjugation. I conjugate the identity by G. What letter do I substitute by E?
H.
H. Okay.
G. So just the identity of.
If I conjugate the identity, if I do G times E times G inverse, what do I get? Does E do anything?
Nothing.
Okay, so then what's GG inverse?
The identity.
The identity, yes. Which is why if you take the derivative of that map at the identity, that gets mapped to the tangent space at the identity.
Yeah.
So that's why that map is in fact an automorphism. well, sorry, that's why it's a map from the tangent space to tangent space. You would still need to say something about this map. Oh, but then conjugation is like some invertible is an invertible linear map, right? Yes, conjugation is an invertible linear map, and it's invertible everywhere. So by inverse function theorem, that has to be full rank, I think, somehow. Like, some words can be said. That is indeed an invertible linear map. Like, it is.
That's the thing. Okay. Multiplication is nice, so surely conjugation is also nice. Okay. So homomorphisms also respect this. So the thing I have written down is d rho of add gv is equal to add, and this is ripped straight out of the book. So I admit I did not do this myself. So this is like kind of weird, but if we stare at it sufficiently, I stared at it sufficiently and then it made sense to me, and then I don't think I wrote down why it made sense to me. So we're going to stare at this for a second. So the adjoint representation, GV. So this is the differential of conjugating, differential conjugating G applied to V, and then we take d rho of that. So this thing lives in the tangent space at G, right? In some sense, this is the differential of the conjugation, and then this thing is going to send it to the tangent space at H, because d rho, if you remember, is the tangent space map between the tangent at G and tangent at H. And here, we are immediately in H, and we are immediately in tangent space H. And the adjoint representation, basically, we are already in H, and then we do it. So yeah, tangent H again. Do you have a picture for this? It's the same picture.
Hold on. Let me think about this. Sorry, we're doing this.
Commutative diagram.
Sorry, this is not in that last thing. Oh yeah, that last whole thing is in the tangent space of H. That's right, I think.
I should say.
Sorry, I'm trying. Wait, it's a little hard to see what's written there because of the glare. But that's okay. Hold on. D rho. Sorry, why do you have D rho?
Sorry.
So it says D rho add GV. What is D rho? What is rho?
Rho is the underlying homomorphism, and d rho is its differential. Push forward, whatever.
Okay. This is right. You have some homomorphism, and the claim is right. You have different adds. I see. Yes. Okay. Yes, I agree.
Yeah.
So let's try and see why this is, of course, true. So.
Where's the picture?
No, the picture's fine. Okay, let me try and write something maybe.
There might be space here.
Yeah, there's space here. So yeah, let's draw the same picture again. Yellow and green. I have your circles are better than mine. Mine are circles and you have like fun shapes. Okay, we have G and H, right? And then we have the identity here, we have the identity here. Okay? Then what do we have? We had, suppose we fix some G in here. Then I have some conjugation operation. This was psi g, right?
Yes.
I had some psi g operation. Do you agree? This psi g operation takes this tangent space, okay, and then does something to it. Okay, it maps it. It maps this tangent space in some way back to itself. Okay. The tangent space gets mapped by what map? By precisely this add g thing. Add of g, this is some linear map that takes the white tangent space and then does something to it, and sends it back to itself. I drew it as a rotated thing, but as this white tangent space got mapped back to itself. It may have been rotated, may have been something, whatever it was. Do you agree? And then what do we want to do? Okay, and then we have this map rho. So let's try and see what is this map? This map
Uh-oh.
Exciting. Oh, you know why it's not turned on? Because I didn't plug it in and it ran out of battery. And this meeting has ended. Okay, the recording is still going. At some point, I don't think it ended too far ago. So hopefully we didn't lose too much.
Surely.
Definitely lost the Zoom people if we had it. Let's start this meeting again. Sorry. No. Okay, let's just capture. Oh, I can do share region. And this time I can do a much better job. Okay, good. Yeah, this is my bad. Okay. Right. And so what does this being equal to this mean? This is essentially saying that if I take the derivative of this, like this way, versus if I take the derivative this way, I get the same thing, right? So this is an important notice. This is add in H, and this is the add in G, and this is the add in H, right? So if I do conjugation by G, take the derivative of that, then take the derivative of, and then compose that with the derivative of rho. That's the same as doing a derivative of rho and then doing a derivative of the conjugation at rho of D. Yes?
Why is the left side the derivative of the composition and not like dp applied to?
This is a linear map. I apply this linear map, and then I apply this linear map.
And why is that the derivative of the composition?
Why is the derivative of the composition?
Yeah, that's
Chain rule. Sorry, I don't understand your question. Say it again. I'm not listening to you.
The first line, it says E rho applied to something.
Yes.
And the stuff that's in the red, it's E of rho composed with something.
Yes.
And
This is rho composed with this conjugation map.
Yeah.
This is a map from the given a fixed G. This is a map from the group to itself. This is a map from the group to H. Agree? So I can compose these maps, and then I can take the derivative of those maps, the Jacobian.
Why is it the same as the line?
Difference between DP and
Sorry.
capital D, and then
He wrote a lowercase d, I wrote a capital D because I wrote a capital D and he wrote a lowercase d.
Yeah, but if you apply chain rule with the stuff that's in red,
Yes.
VG evaluated at like it's the white thing times d phi.
So the derivative, I do derivative of this composed
Right.
with derivative of this. Yes.
I think importantly, maybe I should have written d rho at the identity.
Repeat your question again.
So like when you take the this first thing is taking the differential of rho, and then evaluating on conjugation by G, but applied to the identity, which is just the identity again. So that that entire term vanished into here.
So this is the derivative of this guy, and then this is the derivative of this guy. And so I compose Jacobians.
And then your chain rule went into here.
Yes.
Okay.
And this maps from the identity to the identity. So
Hold on.
does that clear up your confusion? Okay. So you can do the maps in this order, or you can do the maps in this order, or you can do the maps in this order. And so you can either compose the derivative of this with the derivative of this, or you can compose the derivative of this with the derivative of this, and you should get the same answer because it's the same map.
Fine, it seems confusing, but I have no questions to ask. I'll say that.
Okay. Do you just?
I mean,
It's the second part. Like I'm trying to say why the adjoint representation is just the derivative of
Why?
like psi of g.
Why?
the derivative
Because I defined it to be that.
Yeah, exactly. Like, so wait.
it's defined to be the derivative of psi by
Yeah.
definition.
Okay. So we have this, and this is great. This is cool. This is awesome. We have automorphism of the tangent space, which is like nice, but we still have this ugly normal G thing in there, which is not nice. Because to reiterate, we want to get entirely into the tangent space and not have to think about the group itself. So how do we get from this thing in the group to the thing in the tangent space? Does anyone have any guesses? I am putting no money on this.
Is it the thing you wrote in blue?
What did I write in blue?
Like the bracket or whatever.
Oh well, no. We want to get from this adjoint representation to something that lives entirely in the tangent space. We got close because the output of the adjoint representation is an automorphism of the tangent space, but we still have to put this thing from the original group in the input, which we don't want to have to deal with if we're just going to talk about the tangent space. So how do we get from a group to its tangent space? What can we do to this operation? Well, you'll never guess. We'll take a derivative.
Yes. You've taken derivatives before, but what's the point? The point, let's summarize again. Remember before, we're like, I want to understand the structure of the Lie group. For a connected Lie group, we realize it's sufficient to understand the structure kind of at the identity. Even better, it's enough to understand the structure at the tangent space, right? And what structure do I want to understand? I want to know how to multiply elements with each other. Actually, it's sufficient to know how to conjugate. Like knowing how to multiply things is the same as knowing how to conjugate everything. It turns out. And so then, wait a second. Maybe I just want to like specify how this conjugation map works by giving some data about how things are out on the tangent space. Really, like I somehow want to fully encode this conjugation map with information at the identity. So we took one derivative, and we're like, okay, if we take one derivative, then for every element G in the group, we get some linear map on the tangent space of the identity. But that's still not good enough. I want to have information that's like completely on the tangent space of the identity. That adjoint representation, it still involves information about the rest of the group somehow, right? The inputs are in the rest of the group. I want something that's like completely just a linear map from the identity to itself.
So we need something from the identity to G.
Well, no. You don't want anything to do with G. I want to have all of my information to be somehow encoded in something that only talks about the tangent space at the identity and nothing else. And then, okay, we have something that goes from G to the tangent space to something on the tangent space. And then you're like, wait a second, it goes from G, so I can just take a derivative at the identity again. And then that should still have all the information, right? Because this adjoint representation thing, it's a homomorphism as well. And it's also a homomorphism of Lie groups, right? Because the automorphisms on the tangent space, invertible linear maps, that's the general linear group. That's Lie group, we know that. And so the add thing, that's a map from a Lie group to a Lie group, and it's a homomorphism, which you can check because the composition works correctly. So, okay, if I want to, now I realize I apply the first principle again. My first principle, if I want to encode everything about this map, right? So this map encodes everything about conjugation by the first principle. So, but then I say, okay, what if I wanted to encode this map? And then I can apply first principle again. If I take the derivative at the identity, then that will still have all the information about this map. This map had all the information about conjugation. But once I take the derivative here, that will be an honest thing that is like only defined on the tangent space. Keep going.
Okay, so pretty much we take the differential again. The book doesn't even give this a proper name. It is that.
We're calling it lowercase a.
Yes.
Yes.
That's not confusing at all when verbalizing it. But it's a map from tangent space to, okay, well, we have tangent space at G, which was tangent space at G. What on earth is the tangent space of the automorphism group with tangent space at G? So we have a bunch of like, okay, just think, let's think in terms of vector space. So
can you turn
oh,
the
yes,
laptop
true.
a little bit so it can at least see your back?
nice, nothing is visible. Actually, it's a little bit visible.
That's
It's okay.
fine. You're just pointing.
Yeah.
Already.
So we have all the automorphisms of the tangent space of G, which, if we remember, is all the invertible homomorphisms from V to V, or linear maps, whatever you want to think about it as. Well, all the invertible stuff is not exactly a full vector space, right? Because you can like add and subtract invertible maps together, and you can get something that's not invertible, right? You could subtract a map from itself. That's clearly not invertible, it's to zero. So we want the space that is just all of the maps. So this is what we call, I guess I'll put it over here, the endomorphisms of V.
We need to have a Google Doc printed every day with all the morphisms. There are like 5 now.
You're here for a few more years yet.
Yeah. You can remember that.
Well, you remember all the ones you'll have heard about now, and then you'll like know more.
And also, like all of there's really only two things. There's like homomorphism, and then there's isomorphism.
Which are like basically just homomorphisms
Yes,
anyway.
And the rest are like the same word.
Is there a way you can very easily remember what they preserve? Like for example, if it's a linear map, it's invertibility. If it's
Well,
if it's for topologies, well, preserve topology. If it's
Yes.
homomorphism, is about the Lie group operation. Well, that's kind of obvious.
you remember it by like doing it so much, you don't have a choice. Okay. That's fine. Okay. Moving on. So where were we? Right. Endomorphisms. So it's basically same thing, but you might not be invertible now. It's just more general. It's a tangent space. Don't worry about it. Okay. So we are now in this language, and we are finally only in the tangent space. This is great. And we are going to define the Lie bracket. And it's written as a bracket, 2 entries. I should make that comma bigger. And pretty much bracket xy is just defined to be this. Right? Because this lowercase add, you put in a tangent vector, it gives you an endomorphism of the tangent space. So you put in another tangent vector. And this is now going to give you yet another tangent vector. So it's a bilinear map. You put in 2 tangent vectors, you get a new one.
And not just that, it's bilinear. It's a linear.
Well, if I do the group operation here is composition.
What group operation?
Sorry, I'm like my brain's stuck on like add of parenthesis x close parenthesis y close parenthesis.
Sorry, add of what are you looking at?
He's confused as to
I'm
what the
checking,
notation
yeah.
is.
Which one here?
On the left, on the right. Yes.
Oh.
You got it.
So add x. So you put in x. X.
Yeah.
Okay, I should say. X, y are tangent vectors at the identity of G. So you put in an x. This is your x thing. Your add spits out an endomorphism of the tangent space. So what do you do with an endomorphism of the tangent space? You put in another vector, and you get a vector out of that.
Yeah.
So this,
Maybe I misunderstood what endomorphisms are. Are they the set of all homeomorphisms?
No, no, no,
it's
no.
this, but you're not invertible, not in general.
It's just linear maps from V to V. Just
Okay.
linear operators on
Okay, that's better. Thank you.
homomorphism.
Did I write homeo?
Homeo, there's
I wrote
no.
homeo.
So, how do we think of this? Let's just remember. It's a like easy way to remember. Remember, we had this. Remember, we had this conjugation map, right?
Yeah.
In some sense, this was really a map with two entries. Do you agree? It had an entry G and it had an entry H. Do you agree? So, in some sense, this is a map where I can like change around two things and I still get out a member, an element of the Lie group. So, we first took a derivative with respect to H, and then we took a derivative with respect to G. Okay? And so the question is roughly like, okay, suppose I changed around H a little bit with Y, and then I changed around G a little bit with X, right? What is that change overall? And that's what the Lie bracket tells you. If I change around H a little bit and change around G a little bit, what is the overall change? Like, what is the overall little change? That's what the Lie bracket tells you. Right? I took a derivative with respect to this, I can plug Y into that. And then I took a derivative with respect to G, I can plug X into that. So, right. If I take a derivative with respect to H, that gives me some linear map from the tangent space to the tangent space, right? Then I can take a derivative, then I can take X and take a derivative of that linear map in the direction X. I get another linear map, and then I can plug stuff from wiggling this into that. I don't know. Maybe that made sense. Maybe that didn't. But the point is, these two entries correspond to wiggling this and this. And so if I combine those two, then I see what the overall change is in those results.
Okay, and if we briefly refer back to the second principle, which we now understand, surely. So if your manifold is like, reasonable, your linear map, which your linear map of choice between the tangent spaces can only have this form if it preserves the Lie bracket. In the sense that d rho at the identity of xy is equal to, well, it's the exact same kind of structure as we've written before. It doesn't matter what order you do it in. So this is your condition on when linear maps between the tangent spaces of G and H can be written as differentials of ordinary homomorphisms between the Lie groups.
A little bit before, it should look the same, or it should behave the same as you transform it, and then the wiggle a little bit after.
Yes. So, yes, and that is more or less the thing that we wrote down here, right? It's the same idea, right?
Yeah.
I can do those linear maps like this, or I can do linear maps like this, and that's just rewriting that equation in this new notation of Lie brackets.
Yeah.
General question, maybe not connected to this, but we always say like preserve. Is preserve to some essence synonymous with like commutative? Because when we say preserves,
No.
Commutative diagram in that sense?
No. Yes, but not really. Like only very spiritually loosely.
Yeah, people will get angry.
It's like commutative under composition,
Yeah.
maybe like some something
whatever operations.
something was something before, and then after you map it, it's still that something. But it's not necessarily an operation that commutes. It's more like this was this kind of object, and after it gets mapped, it's still that kind of object.
If you want to see the commutative diagrams, they are in the textbook section. I just didn't include them here because
Take a lot of space.
And also, yeah, things don't always like necessarily commute. Because like for continuous maps, it's not that if something was here and something there. It's like if something is here, it came from something there, and so it's not.
Okay. So we've just spent. I honestly I don't have a time, but we spent a significant amount of time going through this, and great, we have achieved our calculational device thing. Now the problem is, how do we do anything ever? Because I'm not doing all that again every time I want to compute a Lie bracket. That would be ridiculous. So we are going to just, actually try and do something with this and see where it takes us. Like, what does this thing actually do? Because we've just said this is a thing that kind of does what we want it to do. What does it actually do? Don't know.
How does it look like?
Yeah.
At the end of the day, it's just you take two derivatives.
Yeah. Okay, I'm going to erase this. I'm going to keep that up.
Yeah, sure.
Yeah?
Actually, sorry, what are you about to do? Are you about to write down like matrix conjugation and take derivatives of that, or something else?
I'm getting to the commutator thing.
Yes, okay, good.
It's just on like why the commutator operation we saw, I don't know, 5 weeks ago was like a special case of the bracket.
Yes.
Okay.
Is it?
It is, the commutator is the Lie bracket for the general linear group. So like for any matrix group.
Commutator in other contexts.
So and in fact, usually like commutator and Lie bracket are just synonymous. Like, you can usually
All right.
just use the same one.
Okay, well, spoilers, but yeah, we're going to show that Lie bracket is basically just a commutator. It is just a commutator. Yeah, so we're now going to say for matrices, we compute Lie bracket. So our group is going to be the n-dimensional general linear group for R. Okay. So, there was a couple notes the textbook wanted to make. So conjugation does extend to, like, outside of this Lie group, you can extend it to the more general space of just all n by n matrices by exactly the same formula, right? There's no reason it needs to change. And this same general space.
Sorry. But to all matrices? No. Because I need invertibility. So I can conjugate
Like
any. So the point is, I can take any matrix and conjugate it by something from
by here.
General
Yes,
linear.
I should have said.
So yes, but
yes. And all n by n matrices, you can write it as like MNR or like endomorphisms of Rn. It's all the same thing, but this is also just the tangent space. Okay. So let x and y be tangent vectors. I'm going to say TEG again, but it's this. Maybe I should write TEG equals that. Okay. So we're going to say let gamma from the unit interval be a map from the unit interval to G. There's going to be an arc in G with gamma 0 equals E, or the like identity matrix, whatever you want to call it, and tangent vector at the origin of x, right? So this is kind of setting up for the conditions we were using earlier. We're gonna work at the identity, and we're gonna have some tangent vector that is going to be one of the ones that we started off with. Okay, then we are going to compute Lie bracket xy. Okay, well, what is this actually equal to? By definition, it's the derivative at t equals 0 of the adjoint representation, oops, spacing, Nope, uppercase, because I'm taking derivative. Gamma of t, and wait, hold on. Did I mess up my brackets here? What is going on? I have one too many brackets somewhere.
That's okay.
This-
I understand.
yeah.
But yes, Y is a matrix. Okay. Maybe you don't have. Maybe your brackets. Yes. What's the thing about gamma? What's the key property? Oh yes, you already wrote it down.
Yeah. Okay. What is derivative? Well. Okay.
So sorry. Let's just clear this up. Y there. Do I have some time derivative? Derivative there. I have something else. Here we wrote it as like composition of linear maps. Here I'm saying instead of just looking at the whole linear map, let's just take a derivative specifically along the x direction. Instead of saying, oh, I could plug in arbitrary x. Just like pick an x and then take a derivative in that direction. Gamma of t is a path along x. So I can just plug it in and then take a derivative of that.
Yeah. So I think the book says that's this. So to take a derivative of this, t is only a variable in these two, so we're just going to do product rule. So this comes out to be gamma prime t y gamma t inverse. And then taking the derivative of gamma t inverse is a bit tricky.
I was gonna say, is gamma invertible?
Gamma is an arc. So we have in our group, this is matrix group. So we're basically taking a path in the group and we're parameterizing it from 0 to 1, the unit interval. Maybe I should write ID. So this is just 0 to 1, right? We're just going to take a little journey.
Oh, it's an interval. It's not one specific element.
No, yeah, it's an interval. It's 0 to 1 explicitly.
All right.
Yeah, you'll see people use this a lot. Okay. Taking the derivative of gamma t inverse. I can go through it if we want to, but it's like the way you do it is I'll write it down in a moment, but it happens to be
Yeah, because we chose x and we're choosing path gamma to be along x, and that way we can just take a derivative with respect to t is just taking a derivative of the x direction.
I'm gonna run out of space. So negative gamma 0 inverse times gamma prime 0 times unfortunate and times gamma 0 inverse close bracket, I think. Yeah. The way you get this, I guess I have space to do that now, is basically just by taking this identity, no pun intended, and differentiating that, and this just pops out. Okay, and well, okay, this is like weird. Okay, there should not be t, there should be 0. I evaluated. Okay, so we now have this monster expression, which is not really a monster because gamma 0 is identity and gamma prime 0 is just x. So gamma prime 0, we got x times y times identity plus identity times y times, oh, sorry, negative times negative identity again times x times identity again. So we get our commutator, and that is the leap bracket in this case. Okay, through page 2.
Going from the bracket xy to the equation, that's just expand the equation. Or no, so not adjoint.
Sorry?
How do we go from this to that?
Oh, because I say this is this, and then I differentiate.
Oh,
Yes. So,
particle.
yeah, it's all no, not product rule that should always be changed. Oh, sorry.
This is multiplication.
Yes. So you have that expression,
Yeah.
and then he just differentiates it.
Okay.
Actually, no. Sorry, it shouldn't be y in there. No, should it not be? Oh yeah, maybe it should be. No, I should have. It should be gamma of. Oh yes. Okay, wait. Gamma t inverse. Yes. That's fine. That's right. Yes. So it's like the details are you're taking a derivative of with respect to h first, plugging in y, and then taking the rest of the derivative. And you get that it's just a commutator of matrix.
Should I erase this?
Are you sure?
Yeah. Okay. So we have basically just seen the lead bracket is like kind of a commutator.
No, it
It is.
commutator.
So
That's it.
yeah. So things that are true of commutators are also true of the lead bracket. What is true of commutators? Obvious thing and like marginally less obvious thing that is obvious when you write it out, which I will not do because it is long. I didn't pull it over, did I? What's going on here?
I think that word just gets stuck a little bit.
Well, okay, it's loose here forever. There will now be hism concealed behind that. Okay, so is skew symmetric? Right. I mean, I don't even need to pull up the form behind this. You remember what it was? I'll write down. Right. Obviously, this is skew symmetric, and it also satisfies the Jacobi identity. Which is, okay, here we go. Bracket x yz plus y z x plus z x y equals 0. Yeah. So those are true.
Yeah.
That's obvious. That's also obvious if you expand it. Okay. So we define the following. And now I finally get to say the words that this thing is about. Lie algebra. Okay. So Lie algebras are usually written with like fractal lowercase characters, which basically just look like normal characters if I write them normal on the board. So I'm gonna do like weird things. A Lie algebra. So this is my factor G. Okay. Yeah, G is a Lie algebra if G is a vector space. With a skew symmetric bilinear map. I wonder what I'm going to call it. Bracket. Yeah, into G.
What typeset is this?
Sorry?
What typeset do they use for?
Fractor. Satisfying the Jacobi identity. So that's what a Lie algebra is. It's a vector space that has that. So I think one of like the really obvious easy examples that came to mind. Well, you can also have a vector space where this just always evaluates to 0. That's skew symmetric. That satisfies the Jacobi identity. So
No, but it's not like
yes, it's true. So that works. You can also consider R3 with the cross product.
Which what Lie group has that kind of Lie algebra?
Probably the Lie group that's also the Lie algebra.
Oh, it's I don't know, maybe the like real numbers under addition or something like this.
Something easy.
I don't know, so something easy. But this is actually a good point. So initially, sorry, not a good point. I'm just gonna say something unrelated, completely no. We started off with like a Lie group which had some manifold structure and everything. And then we managed to kind of fully distill this information.
Sorry, no. You mentioned R3 and the cross product. The cross product is our Lie bracket.
Yes.
Yeah.
Okay, it's really funny because the first week of 240, if you'll remember, there was an innocent little first year in way back in my hall asking the professor, saying, "Hey, is the cross product a thing? Like if it satisfies like some product?" Say, "No, sorry, you'll see that in third year." This is why now I like. Okay, sorry.
Yeah, 367 is third year
Boom.
class.
So
Boom. It makes sense though.
Right. Before we had something about like Lie groups, and we found Lie algebra. Like we show that every Lie group has a Lie algebra, and if the Lie group is simply connected and simply connected, then it has then it's like fully determined by this Lie bracket.
Yes.
And so actually the opposite is true. If I just give you Lie algebra, meaning I just give you like a vector space with a Lie bracket on it, then out of that you can construct a simply connected Lie group. So if I just give you a vector space with like some commutator looking thing defined on it, then from that you can build a Lie group.
That can't be true. Really?
That is true.
Oh, I guess the other ones
Like,
aren't connected.
This is like we went one way, and in fact, going the opposite way is true. But going the opposite way is harder.
What's the group operation? Or can you determine the group operation through this like inversion? I guess.
That's what I'm saying.
Yeah, that's the
I'm
goal.
saying is that this is precisely what you can do.
Like
That
if
this like encodes all, and you can do this in a unique way. So that the Lie algebra
So
essentially fully captures all of the information about your Lie group if it's simply connected. And I guess it's what does it do? I guess if you had like a Lie group with different connected components, then maybe it like just tells you something about a single connected component. But I'm not sure if that's true. I need to think about it for a second.
Yeah, the point was if you have a vector space map that preserves this in the sense that then you know that it comes from some underlying row between Lie groups, and presumably you can find that row. Presumably, I can't. But. Okay, and we are going to go through a slightly less obvious example of Lie group Lie algebra.
What's the other example you want to do?
Let's see. It was orthogonal group.
It's all the same. Do you want to do it, or do we want to call it?
It's quick. I can just write it down and like not explain anything. I have like 3 lines of LaTeX. Okay. So we're going to be looking at the orthogonal group. What is the orthogonal group? So they preserve. Okay. A is in the orthogonal group. This is a matrix group, by the way, n-dimensional matrices. If we're going to use the usual inner product because don't worry about it. Yeah. I think. Yes. Okay, cool. So let A sub t be an arc. So an arc is just as before, right? We're going to take another path through this place. So by definition, for all t, this must be true. All t, all VW. Okay, that's cool. If we take a derivative, oh, right, sorry, hold on. I should write, this is the identity matrix, and A0 prime is equal to x. Yes, okay. So take a derivative of both sides of this.
What's the direction here? A0's, okay, A0's, I get it.
Yeah. So we take derivative, and through process, we get this. The process is obvious, but I could say it, but looks like we're running out of time. I really have not looked at the clock.
It's fine.
Okay, and that's equal to 0 because that's a constant. So okay, if that's 0, this is 0. So what do we find? This condition tells you what x are allowed to be in the Lie algebra, right? Because if you have an x in the Lie algebra, you can construct some arc that has its derivative being this. If your x doesn't satisfy this, you cannot be in the corresponding Lie algebra to the orthogonal group. Yeah. So this is also true. A times A transpose is the identity. So differentiating that gives the condition x transpose plus x equals 0. So that's another equivalent condition to this. So, well, what does that tell us? Well, that tells us that the Lie algebra for the orthogonal group is all of the skew-symmetric matrices.
Anti-symmetric.
Okay. So I think the book called it skew-symmetric, but yeah, anti-symmetric.
I would say I would call it anti, but maybe different. I don't know the difference. That's why I call it anti-symmetric matrices because I know that's for sure correct.
Yeah. So yeah, this is the subspace of all matrices that are anti-symmetric, and that is the Lie algebra for the orthogonal group.
And you may recall that lecture 5 of our quantum mechanics reading group, this is precisely what we did as well. Like we did the exact same calculations right there.
My brain fails me. What's the topic thing on it?
I think it was called weakness.
What did you do to them?
The quantum mechanics. Yeah, Schrodinger equation of the groups. The quantum mechanics reading group for them was slightly different than for you guys. No, that wasn't me. That was mine. Because I think we had an extra day and I had nothing prepared.
So you decided to. Were you trialing this one?
Well, I was like thinking. I was thinking. No. That was like.
Yeah. Okay.
Okay, we're done.
We're done.
Hopefully this recording has.
It has continued.